Hello everyone and welcome to another lesson. In today's lesson, we will be talking about confidence interval estimation, and this is chapter 8. So in today's lesson, the learning objectives. First, we will be talking about point versus interval estimates. Second, confidence interval estimates for mean. Third, confidence interval estimates for proportion. And finally, we will be talking about determining required sample size. Accordingly, the lesson has been structured into 4 sessions. The first session will look at point versus interval estimates, confidence interval estimates for mean, and confidence interval estimates for proportion will be your second and third sessions. And finally, we will have a look at determining required sample size. Right, let's have a look at point versus interval estimation. So, what is a point estimate? It is basically a single number. You say a point means a single number. A confidence interval or interval estimate provides additional information about the variability of this particular estimate. So from an interval estimate, you get a range of numbers. Point estimate, you get a single number. So let's have a look at what this looks like visually. So here you have your lower confidence limit, upper confidence limit, and here you have your point estimate, and this here is the width of the confidence interval. So this could be your point estimate and this is your confidence interval. So you see your confidence interval or your interval estimate gives you a range of numbers, whereas your point estimate is only a single number. So point estimates, so for population parameters mean, mu and proportion pi, all this time up to chapter 8, we've been estimating these population parameters using sample statistics of x bar and simple p. So this is our sample mean and sample proportion. So these are examples of point estimates. So these are point estimates. These are estimating the population parameters. Now from here onward, we'll be talking about interval estimates. Now there is a lot of uncertainty with regards to point estimates for population parameters. Now an interval estimate provides more information about this particular population characteristic. So such interval estimates, we call them confidence intervals. So these intervals gives a range of values, and the important fact here is these are all in terms of levels of confidence. That is important. So confidence interval, let's have a look at an example. So in practice, you only take one sample size of n. That is what you have been doing all this time. And in practice, you do not know your population mean. So you do not know if the interval actually contains this population mean. However, what you know is 95% of the intervals formed in this manner will contain mu. So what we are doing here is we are going to have a range of intervals, and out of all those intervals, 95% of those intervals will contain mu. That is why we talked about that confidence level in the previous slide. Now, based on the one sample you actually selected, you can be 95% confident your interval will contain mu. This is a 95% confidence interval, right? So 95% confidence is based on the fact that we used Z equals 1.96. Remember, in the standard normal distribution, when you have 95%, on either side, since it is symmetric, you would have 2.5% on your left hand side, lower tail, and upper tail would also be 2.5%. So what I'm talking about is if you were to draw this standard normal distribution like this, right? Here, this area is 0.95. Therefore, this lower tail and this upper tail would be 0.25 respectively, and therefore when you go and look at the Z table, this value here you would get minus 1.96 and this value you would get plus 1.96. Right. So the estimation process, you have your population. So you have your, say, the population mean, which is unknown. You take a sample from this, and then from that sample you consider the random sample of, and the mean to be 50. So this 50 is your sample mean, random sample mean. So then you can say, I'm 95% confident that your population mean is between two values, between 40 and 60, because your sample mean is 50. So you can say you're 95% confident that your population mean is in between 40 and 60. So in general, what does the formula look like? Well, you have your point estimate. For example, the point estimates for sample mean, sample proportion, likewise, plus or minus a critical value, right? So this critical value can be obtained through your Z distribution. Then you will be studying about T distribution in this chapter as well. So those distributions will give you the critical value times the standard error. We will be talking about the standard error in due course at the end of this chapter. So a point estimate is the sample statistics. Like I said, the sample mean, sample proportion, likewise. The critical value is a table value based on the sampling distribution. So your Z table or a T table. And standard error is the standard deviation of the point estimate. So here you have confidence level and confidence level 1 minus alpha. Confidence level is basically the interval will contain unknown population parameter. So in this 1 minus alpha, suppose your confidence level is 95%, then 1 minus alpha is this 0.95. So alpha is 0.05. Now if I were to draw this, how would this look like? So if I draw the standard normal distribution, say I draw the Z distribution, right? And I'm told that 1 minus alpha is 0.95. So that would be this area. This area is 0.95 or 1 minus alpha. And the remaining area, which is this lower tail and this upper tail, the addition of that would be 0.05. So therefore, you have to understand individually these two areas would represent alpha divided by 2, and this is also alpha divided by 2. Right? So that is what's being said here. Let's move on. Now let's have a look at actually figuring out the confidence interval estimates for the mean. So in this case, when you're calculating confidence intervals, you have two main areas. You're calculating confidence interval for the population mean and population proportion. In this section, we are talking about population mean. That also is further subdivided into two areas where population standard deviation or sigma is unknown and the sigma is known case. So here we'll be talking about the sigma known case. So what are we doing? We are forming confidence intervals for population mean in the case of your population standard deviation being known. So here I have inserted a video which you can watch, and this is by JB Statistics. This video will clearly explain through graphics and visualization as to how you calculate the confidence interval for population mean when your population standard deviation is known. Right. So the confidence interval for your population mean mu when your sigma is known is given by this particular equation. So there are a few assumptions as well. The population standard deviation is known. population is normally distributed, and if population is not normal, you have to use a large sample. So the confidence interval estimate. So the confidence interval estimate is for population mean mu, and that is given by x bar, that is your sample statistic, or in other words your point estimate, plus or minus z alpha over 2, right? This is your critical value times your sampling error, which is given by sigma over root n. So x bar, as I explained, is the point estimate. Z alpha over 2 is the normal distribution critical value for probability of alpha over 2 in each tail, which I drew in the previous slide. And sigma over root 10 is your standard error. Right, so finding the critical value, consider 95% confidence interval. So in that case, your Z alpha over 2 would be plus or minus 1.96. So if I were to draw this, here you have your Z units. On this side you have minus 1.96 due to symmetry. Here you would have plus 1.96, and this area, the area I've demarcated in yellow, is 1 minus alpha, or in other words 0.95. So your alpha would be 0.05, therefore your upper tail and your lower tail would be 0.025 simultaneously, right? Because when you add these two, you would get 0.05 plus the middle area is 0.95, and the total addition comes up to 1, the probability of 1. And this here would be your lower confidence limit, and this is your upper confidence limit, and this single digit value or the single number is the point estimate. So the sampling distribution of the mean. Now here you have your mean of means, or your, which is equal to your population mean. So remember, we talked about this sampling distribution of the mean under chapter 7. And here you have alpha over 2 on either side, and in the middle you have 1 minus alpha. And here you have several confidence intervals, and the intervals extend from these two values. Remember, the equation pertaining to confidence interval for population mean is given by x bar plus or minus z alpha over 2 times sigma over root 10. So the values range from this value x bar minus to x bar plus this value. And 1 minus alpha times 100% of intervals constructed would contain your mu, and alpha times 100% do not contain your mu. So when I say 95% confidence interval, I'm actually talking about 95% of the intervals that you have made contain your population parameter, whereas 5% of those intervals do not contain your population parameter. That is what this says. Right, common levels of confidence. So throughout, mainly we use these 90%, 95% and 99%, and the corresponding Z values are given here. For 95%, it is 1.96 Z alpha over 2, 90% is 1.645, 99% is 2.58. You don't have to remember these, but as you go along and as you do a lot of sums, these numbers will be very familiar to you. Right, let's have a look at an example now. So you're given a sample of 11 circuits from a large normal population has a resistance of 2.2 ohms. We know from past testing that the population standard deviation is 0.35 ohms. So what's the question that they're asking? Determine a 95% confidence interval for the true mean resistance of the population. So let's have a look at how we go about answering this particular question. Right, let's have a look at how we solve this. So here, let's underline the key things that we need. It says it has a mean of 2.2, and from past testing, population standard deviation. So the population standard deviation is given, right? And what are they asking for? Determine a 95% confidence interval for the true mean, right? So we know the population standard deviation. What they're asking for is the confidence interval for the true mean. Okay, so we know the equation for this. That would be x bar plus or minus z alpha over 2 times sigma over root n. Why did I choose this z? Because the population standard deviation is known, so therefore we can go for the normal distribution, right? So they are saying a 95% confidence interval, and if we draw the normal distribution like this, what they require is this area over here represents 0.95 probability or 95%, and therefore this area and this area individually represents 0.025 and 0.025. So the area representing 0.025, if you take your normal distribution table, 0.025, you will notice it is at minus 1.96. The closest value is this. So that is minus 1.96, right? This value. So I underlined, so I made a mistake there. I underlined minus 1.95. These mistakes can happen when you are looking at the table, right? So ensure that you're correctly identifying the value that you require. So I required 0.025, and that is minus 1.96. So here it is minus 1.96. Since it is symmetric, this is plus 1.96, right? So simply just substitute the numbers. We know what x bar is. X bar is 2.20 plus or minus. Z alpha over 2 is 1.96, right? Plus or minus. That's why you have the plus or minus here because of this. Times sigma is given, population standard deviation 0.35, divided by, you are told that a sample of 11 circuits, divided by the square root of 11. Now if you were to solve this, what you would get is 2.20 plus or minus 0.2068, right? Therefore the two values would be 2.20 minus 0.2068 and 2.20 plus 0.2068. So your population mean or your true mean would lie in between 2.4068 and 1.9932. So how do we interpret this? Well, we are 95% confident that the true mean resistance is between 1.9932 and 2.4068 ohms. Right, so as we saw there, we use the confidence interval estimate for the population mean mu equation, and we substitute the values, and we got the answer for the population mean mu being in between these two values. So how did we interpret that? We are 95% confident that the true mean resistance is between 1.9932 and 2.4068. Although the true mean may or may not be in this interval. 95% of intervals formed in this manner will contain the true mean. So that is very important to understand, because we are 95% confident that a true mean resistance is in between these two values, but the true mean may or may not be in this interval as well, because 95% of the intervals that you form in this manner will contain the true mean. That is for sure, right? So this interpretation, looking at this in two perspectives, is very important, because that gives you a better understanding about what this confidence interval, story behind this confidence interval is. You're looking at it in two angles. You're 95% confident that the true mean is between these two values. However, the true mean may or may not be in this particular interval. So 95% of the intervals that you form, so this is one interval, you can have more intervals. So say you form 100 intervals, 95 of those intervals will formed in this particular manner will contain the true mean. 5% may not, right? So we were talking about confidence interval for population mean, and we looked at the sigma known case. Now let's have a look at when your population standard deviation or your sigma is unknown. So again, I have attached a video here. This is through the YouTube channel JB Statistics. So this video also goes into detail about the confidence interval estimation for population mean mu when your population standard deviation is not known. Right, so you actually don't know your population standard deviation. In most cases, in pragmatic cases, you would not know this. Because if you know your population standard deviation, basically you would be knowing your population mean as well. Because in order to calculate the standard deviation, you would need the population mean as well. Right? So basically what I'm trying to say is, in pragmatic or practical cases, in the real world, you would not know your population standard deviation. So then in that case, how would you calculate your confidence interval for your population mean mu when your sigma is unknown? Now, if the population standard deviation is unknown, we can substitute it by the sample standard deviation, right? So now this, by substituting it by sample standard deviation, it introduces extra uncertainty, since S is a variable from sample to sample. So your sample standard deviation varies from sample to sample. Say you have 4 samples, your first sample standard deviation might not be the same as your second sample standard deviation. And your second standard sample deviation might not be the same as your third sample deviation. But your third and fourth sample standard deviation might be the same. So you don't know, it varies. So that is why it says it introduces extra uncertainty. So therefore, in that case, we use this t distribution instead of the normal distribution. You use the t distribution instead of the normal distribution. So what are the assumptions? Your population standard deviation is unknown. Population is normally distributed. That is very important. And if your population is not normal, you must use a large sample. And you're going to use the student's t distribution, and accordingly, the confidence interval estimate is given by this equation. Now, this is quite analogous to the first equation that we had a look at. The only difference being, here you're considering the t distribution because you don't know your population standard deviation. And since you don't know your population standard deviation, you're using the sample standard deviation. Right. So the student's t distribution, what's important to remember is it is a family of distributions, and it depends on this. Now you're going to learn a new concept, degrees of freedom. So this t values depends on these degrees of freedom, and in this case the degrees of freedom is calculated by the sample size minus 1. So number of observations that are free to vary after the sample mean has been calculated. So in this case, degrees of freedom is your sample size minus 1. But let's have an intuitive understanding of what these degrees of freedom mean. Now, basically the idea is the number of observations that are free to vary after sample mean has been calculated. But when I say it like that, you might not understand it. So let's have a look at an example. So suppose the mean of 3 numbers, or the average of 3 numbers, is 8. So let's take the 3 numbers as x1, x2 and x3. Right? So let's take x1 to be 7, x2 to be 8. Then you asked what is x3. So if the mean is of these 3 is 8, x3 must be 9. That is the critical term here. x3 must be 9. So in other words, x3 you can't vary it. It is not free, right? Because your average of these 3 numbers are 8. you're told that x1 is 7, x2 is 8. Then what is x3? If that is the case, x3 should be 9. But if you change x1 and x2 to another set of numbers, again, accordingly, x3 should be a number such that the average is given by whatever value it is. So in this case, x1 was 7, x2 was 8. It was freely chosen. There were no restrictions. But you're told the average is 8. So then x3, you can't freely choose any number. It should be 9 and 9 only. So that is why, and that is how this degrees of freedom, the idea behind degrees of freedom comes about. So here, your n is 3. You have 3 numbers. So your degrees of freedom, you can vary 2 numbers, x1 and x2. So 2 values can be any numbers. That's what I said. But the third is not free to vary for a given mean. The third value is not free to vary or change for a given mean. So that is about degrees of freedom. Now, students, t distribution, what is important to keep in mind is your t distribution approaches your z distribution as your sample size n increases. So the bigger your sample size, your t distribution will approach the z distribution. So let's have a look at this graphically. So you have your t-axis, and this is for your t distribution for degrees of freedom 5. So in that case, your sample size is 6. Remember, degrees of freedom is sample size minus 1. So if your degrees of freedom is 5, sample size should be 6. And this is your t distribution when your degrees of freedom is 13. So sample size is 14. You see that the sample size has increased. And this here is your degrees of freedom for infinity, right? So as your t distribution, as your n sample size increases, these t distributions approaches the z distribution shape. That is important, very important to keep in mind. Right, so the t distribution table, you have your first column, you would have your degrees of freedom. I will show this when we are doing a problem. So your first column will have degrees of freedom, and then you're given the upper tail area, right? So what's important to keep in mind is these values here are t values and they are not probabilities. That is very important. These values given in the table are not probabilities. They are t values. So let's consider the example of sample size 3. And your degrees of freedom is then 2. Consider the case of 1 minus alpha being 90%. So your alpha is 0.10 and your alpha divided by 2 is 0.05. So you have your t distribution and you have your alpha over 2 as 0.05. So how would you know your t value pertaining to this point here? Well, you know your degrees of freedom is 2. You know your upper tail value is 0.05. So then that value is 2.92. And that is how you figure out your t value for a given area like this, for a t distribution. So this is in comparison with the z values, the t distribution values. Now if you notice here, as your degrees of freedom increase from 10 to 20 to 30, your t distribution slowly but surely approaches the values of your z distribution. And as the sample size grows from 30 to infinity, your t distribution values approaches your z distribution values for the given corresponding confidence intervals. So that's what I've mentioned here. Your t values approaches your z values as n increases. So let's have a look at an example. A random sample of n equals 25 has sample mean x bar 50 and sample standard deviation 8. Form a 95% confidence interval for your population mean. So you're given your sample standard deviation and you're asked to calculate or form a 95% confidence interval for what? For your population mean mu. So then you know you have to use your t-distribution. So let's have a look at how you solve this. Right, so when we are given this particular problem, first let's underline the key terms that we require. You're told the sample size is 25, you're given x bar which is 50, and you're given the sample standard deviation which is 8. Okay, form a 95% confidence interval for your population mean. So since you do not know your population standard deviation, you know that you will not be using the standard normal distribution, that is your Z distribution. What you will be using your student's t distribution, since you're given the sample standard deviation. So if that is the case, we know that we had to write down the degrees of freedom, which is n minus 1. N in this case is the sample size, which is 25 minus 1. Your degrees of freedom is 24. Then if you were to draw your t distribution, right, so you're told to form a 95% confidence interval. So this area here should be 0.95 or 95%. Therefore this area and this area symmetrically should be 2.5% and 2.5%. Right, so then what we require is the value over here. So what is the value over here? We take our table, our t table this time, critical values for t, and you have your degrees of freedom in your first column, and you're given your upper tail areas. So here what we require is this area over here to be 0.025, right? So 0.025 is given by this column. You have 24 degrees of freedom, right? So how do you look at the value? You have 24 degrees of freedom, 0.025, 2.0639. That is your value, 2.0639. So the equation pertaining to this, the confidence interval equation, is given by x bar plus or minus t times alpha over 2. Why do we consider t? Because we don't know the population standard deviation, times s over root n. So x bar is given, which is 50, right, plus or minus 2.0639 times s is given 8, sample size is 25, right? So why do we have plus or minus? Because this value over here is plus 2.0639, and since this is symmetric, over here we have minus 2.0639, right? So because we need two values, we are looking at the confidence interval, so we need two values on either side. So therefore your population mean in this case would lie in between 53.302 when you add this value over here to 50, and 46.698 when you deduct this value from 50, and that will be your answer. Right, so like we did in the calculation, you find out your degrees of freedom is 24, your t of alpha over 2 is 2.0639, and you simply substitute it to your equation, from which you get the interval for your population mean. How would you go about interpreting this? Well, it requires the assumption that the population you're sampling is approximately a normal distribution, especially since n is only 25. Now, if n was greater than 30, you can actually think about the central limit theorem. But since it's 25, you had to assume that you're sampling from is the population that you're sampling from is approximately normally distributed. And how do you check that? Well, you can use a normal probability plot or a box plot. Right, so that is confidence interval estimates for the mean. Next, let's have a look at confidence interval estimates for proportion. Now, we've been talking about confidence interval estimates for population mean, sigma known and sigma unknown. Now we are going to talk about population proportion, confidence intervals for the population proportion which is given by pi. So in this case, if you recall, this is the distribution of the sample proportion is approximately normal if the sample size is large, with the standard deviation given by this equation, and we are going to estimate this by this equation. So pi is your population proportion, simple p is your sample proportion. We are going to estimate this equation with your sample data given by this. So you have your upper and lower confidence limits, and your equation pertaining to the confidence interval of your population proportion is given by this, where simple p is your sample proportion or your point estimate, z alpha over 2 is your critical value, and this is your estimate or your sample standard, your standard error. Right. Here what's important is these two conditions need to be met, where n times p, n is your sample size, p is the sample proportion, the multiplication between n and p should be greater than 5, and n times 1 minus p should also be greater than 5. So let's have a look at an example. You're told a random sample of 100 people have 25 people who are left-handed. You are asked to form a 95% confidence interval. Now you see the question and you see confidence interval. Then you ask yourself, okay, for what do I have to form the confidence interval? For the true proportion, right? Then you have to quickly remember what the equation is for this. P plus or minus z alpha over 2 times p times 1 minus p over n, square root of that. So we are using the z distribution for proportions. You have to keep that in mind. But in the case of population mean, you either have z distribution if your population standard deviation is known. If it's unknown, you would use the t distribution. So when you're given questions in the examination, this is a place where you can go wrong, where you use the wrong distribution, and that results in your whole answer being wrong. So please keep in mind, when you're given the question, read it carefully and see, okay, you ask for the confidence interval, what is it asked for? True proportion. Then quickly make a side note, for proportions you are going to use your z distribution. Right, so let's have a look at how we solve this. Right, so this particular question, you're given a sample size of 100 and you're told that 25 are left-handed. You're asked to form a 95% confidence interval for the true proportion of left-handers. Right, so your simple p would be the sample proportion of left-handers. Sample proportion of left-handers, and that is given by 25 over 100, which is 0.25. So in this case, they are talking about a confidence interval for the true proportion. So in that case, you have two conditions that you have to meet in order for you to use the equation, which is n times p, the sample size times the sample proportion, should be greater than 5. So n is 100, the sample proportion is 0.25, which gives you 25, which is greater than 5. And also n times 1 minus p also should be greater than 5. So let's check that. 100 times 1 minus 0.25, this is 0.75, which gives you 75. So that is also greater than 5. So that ensures that the sample is big enough, because then we can use the standard normal distribution for this. That is, you can use the z distribution. So in this case, your confidence interval, the equation is given by p plus or minus z alpha over 2 times p times 1 minus p divided by root n. Right. So in this case, do we know p? Yes, we do. 25 over 100 plus or minus z alpha over 2 is 1.96. By this time, you should be very confident about this value now, because the corresponding value for 95% with respect to Z is 1.96 times, then let's substitute the values over here. P is 0.25, 1 minus P, 1 minus 0.25 is 0.75, divided by N, sample size is 100. Whole thing square root. So what we are asked for is, what are the two values in between which your population proportion lies. So if you deduct this value from 0.25, you would get 0.1651, and if you add this value to this particular value, you would get 0.3349. So how do you interpret this? Well, we are 95% confident that the true percentage of left-handers, so that is your population proportion given by the symbol pi, in the population is in between 16.51% and 33.49%. Right, so what we did was we looked at the two conditions. Those two conditions were met, and it ensured that the sample size is big enough. We substituted the values to the equation, and we got the answer for pi as these two answers. So from which we can interpret that 95%, we are 95% confident that the true percentage of left-handers in the population is between 16.51% and 33.49%. A side note, although the interval from this value to this may or may not contain the true proportion, 95% of intervals formed from samples of size 100 in this manner will contain the true proportion, right? So we talked about this perspective as well before in one of the examples. So now we have talked about a lot of things. We talked about point estimate versus interval estimates. And then we talked about confidence interval estimates for the mean under two sub areas where your population standard deviation is known and your population standard deviation is unknown. If your population standard deviation is known, you use your Z distribution, and if your population standard deviation is unknown, you use your T distribution. And then we looked at confidence interval estimates for proportion where you use the Z distribution. Finally, let's have a look at determining the required sample size. What is the sample size that is required? And that is your final section. Right, so in this section, we'll be having a look at two areas, determining the sample size for mean and for proportion. But before that, let's have a look at this concept known as sampling errors. So the required sample size can be found to obtain a desired margin of error with a specified level of confidence. This margin of error is this sampling error. So when you are calculating the sample size, you have to have this margin of error, right? So you might not know exactly, but you are given plus or minus value, right? So you're asked to find the sample size, but you're given a margin of error. So that margin of error is your sampling error. So the amount of imprecision in the estimate of the population parameter, the amount added and subtracted to the point estimate to form the confidence interval. Right, so let's have a look at determining your sample size for mean. So how do you go about doing this for the mean, sample size for the mean? So you know the equation. This is the equation for the confidence interval for population mean mu. Now we are going to take this area, right, this section of this equation, and we are going to call it E, and that is your sampling error or the margin of error. Now from this, how do we determine the sample size? It's Zn. So you simply substitute n here, and when you do that, you get this equation. You simply substitute n from here and you get this equation. So this is how you determine the sample size for the mean. Here I have attached a video again which explains about determining sample size for mean. Please do go through this, you will get a better understanding as well. Right, so in order to determine the sample size for the mean, you have to know the desired level of confidence. You should be given the sampling error E and the standard deviation sigma. So let's have a look at an example. You're given the population standard deviation 45. You're asked what sample size is needed. What sample size is needed to estimate the mean within plus or minus 5 with 90% confidence. So what's the question? They're asking for the sample size. Okay. Then needed to estimate what? The mean. Right. Then you have to quickly remember the equation. The equation for the confidence interval for population mean. X bar plus or minus. You're given the sigma. So Z alpha over 2 times sigma over root 10. From that, the sampling error is given by Z alpha over 2 times sigma over root n, and that is your sampling error, E, and here you are given the E, which is plus or minus 5, and you are given the confidence, 90% confidence level, and they are asking for the sample size. So let's have a look at how you solve this. Right, so in this question, you're given your sigma, and you're asked for what is the sample size. Okay, you asked for the sample size that is needed to estimate the mean within plus or minus 5 with 90% confidence. Right, so you asked for the sample size. So in this case, you asked for the sample size needed to estimate the mean. So for mean, you know the equation which is given by this. And why did I consider this equation? Because your population standard deviation is given. So in this case, this value over here is your error term, sample error term, Z alpha over 2 times sigma over root 10. From this, we made n the subject and we got the equation as Z squared times sigma squared divided by E squared. So what we have to do is simply substitute the values to this particular equation in order to figure out the sample size, simple n. So n equals 90% confidence. Right, so then in this case, if you draw the Z standard normal distribution, they are saying that this area signifies 90%. So in that case, since this is symmetric, this should be 5% and this should be 5%, right? So that the total becomes 100%. In that case, if you go and check in your Z distribution, cumulative standardized normal distribution, where you have 0.05, you will notice that you get it at minus 1.6, but there is no 0.05. There is 0.0505 and 0.0495. So it is in between these two values. So what I'm going to do is I'm going to take the average of minus 1.64 and minus 1.65, and I'm going to consider this value as minus 1.645. Since this is symmetric, this is plus 1.645. I have written it to the third decimal. So now I'm going to simply substitute that value. Plus or minus, it doesn't matter. We are squaring it. So 1.645 squared times sigma squared is 45 squared divided by E squared. E is what? It is given plus or minus 5. So it is 5 squared. This will give you an answer of 219.19. So the required sample size is 220. So this is the answer. You have to always keep in mind, always you have to round up, right? So you get 219.19. You round it up and that's how you get 220. Right. You, like I explained in the calculation, you simply substitute the values and you obtain the value 219.19. You round this up and you get 220. That is the required sample size. Now, if sigma is not known, how would you go about it? Well, you can select a pilot sample and estimate your sigma with the sample standard deviation of S. Now let's have a look at determining sample size for your proportion, right? So that is the second area for the proportion. Well, your sampling error is given by this equation, from which you make n your subject, which is your sample size, and you obtain this equation. And here I have attached another video which explains about this concept of determining your sample size for proportion. Do go ahead and watch this video. You will get a better understanding to this concept. So determining sample size, in this case, what is important here is pi, your population proportion. If that is not given, you can estimate it with a pilot sample if necessary. So in your example, you will be given that. Or if that is also not given, you can use 0.5 as an estimate for pi. So you have to make sure that you have to remember this, because that is important when it comes to estimating your population proportion. So let's have a look at an example. They're asking how large a sample would be necessary. Okay, quickly make a note of that. You ask for the sample size. Estimating what? True proportion. Okay. Defective in a large population with plus or minus 3%. That is your sampling error. With 95% confidence. That is your confidence level. So how do you go about solving this? Well, you need another data. That is, because you're not given the population proportion, you're given, assume a pilot sample yields p equals 0.12. Right, now you can solve this. Let's have a look at how you solve this. So in this particular question, you're asked how large a sample would be necessary. So you ask for the sample size to estimate the true proportion, right, defective in a large population within, you're given the error term plus or minus 3% with 95% confidence, and you're also given, assume a pilot sample yields 0.12. So you ask for the sample size to estimate the true proportion with 95% confidence and the error as plus or minus 3%. So in this case, you should remember the equation where your error term is given by z times pi 1 minus pi divided by n, the square root of that. From this, we make n the subject, so we get z squared times pi 1 minus pi divided by e squared. So simply what we have to do is, we have to substitute the values to this particular equation. In this case, you are given a pilot sample and you are told that the pilot sample yields a sample proportion of 0.12. So that means instead of substituting the value for pi, you can substitute the value for the sample proportion of 0.12 in this case. So n equals z squared. So you are considering 95% confidence. So you know it's 1.96 squared times, for pi you would use 0.12. You're going to estimate pi by this simple p times 1 minus pi is 1 minus 0.12 divided by the error term squared. Error term is 3%. So that is 0.03 squared. So you would get the answer as 450.74. So we round this up, hence you get the answer as the sample size of 451. Right, so as we did, you have 95% confidence, so your Z alpha over 2 is 1.96, E is 0.03, P is 0.12. So you use that as the estimate for pi and you substitute the values to your equation and you obtain 450.74. You round this value up such that you get the sample size as 451. So this is the sample size required. 451 is the sample size required to estimate the true proportion for a large population within this plus or minus 3% sampling error with 95% confidence. So that brings an end to this chapter. So let's have a quick recap as to what we did. We talked about point versus interval estimates. Then we talked about confidence interval estimates for the mean in the case of sigma known and in the case of sigma unknown. Then we talked about confidence interval estimates for proportion. And then finally, we talked about determining required sample size. Again, a quick reminder of the reference book. Do download this book and go through the questions in this particular book. And I have also attached the video, this particular video explanation into your PowerPoint. So I have attached two PowerPoint presentations, one in which you have these videos and the other one in which you do not have these videos. And that is it for today. Thank you very much. And as always, dream big and start small. Thank you very much.